our next speaker, who is Magnus. He's a medicinal chemist, and he's going to talk to us about designing drugs for bacterial infections. And he would like you all to know that his fun fact is that he was once set on fire on national Danish television. So you can ask about that if you don't have any questions.
Right. So I will be talking a little bit about how we try to treat our diseases right now that are simply untreatable. So I'm pretty sure we can all agree that medicine is quite important. If we go way back in time and you just got a simple cut on your hand and you got an infection, that could be potentially deadly. But then, we discovered antibiotics. Now if you get a cut on your hand, it gets infected, no problem. We treat it with some antibiotics, quite trivial, and your hand is just fine. It's also this case, for example, for HIV. Used to be that HIV was a death sentence within 1 to 2 years. Now, we have HIV, still not so nice. We have made a lot of drugs for it, which means that now you can live a pretty normal, healthy, happy life. And when you probably think of medicine, you'll think of like pills, you'll think of these like generic names. When I, as a medicinal chemist, think of medicine, I think of these guys, the chemical structures. If you haven't seen these before, just know all these little bends here, they are carbon atoms. And all this NH, that's nitrogen, hydrogen, or O is for oxygen, and so on and so forth. And they're these molecules that interact with the biology within our body to cause some kind of effect. And so really the job of a medicinal chemist like me is to know what is medicine, first of all, what kind of medicine is out there, how does it work, and could we make something that might be even better or at least different. And then we propose, maybe we have some chemical structure, we propose maybe we can change that into something that could be better. And then we go into the lab. This is pretty much what it looks like. You stand in a fume hood like this all day, then you mix liquids and powders, and then you get some molecule out that you analyze. It seems a little bit like magic, but really it's a lot like playing with Lego. Imagine you have a bunch of little pieces, and then you use chemistry to put those pieces together one by one until you get some molecule out that you were trying to make. I'll say the main difference between Lego and chemistry is that for Lego you have to be 5 years old. For chemistry you have to study at university for 5 years. And also putting two pieces together can take anywhere between 1 to 2 days to multiple months, whereas Lego is unfortunately a little bit faster. So it's like Lego if you're a really patient adult. So I told you before that medicine really has revolutionized the world in a lot of ways for a lot of different diseases, but there are actually diseases where this is not the case. So diseases where if you go way back and you got this disease, well, it was very deadly. And now, if you got the same disease, it's still really deadly. And it's actually these types of diseases that I work with. More specifically, I work with what's called implant infections. So you can imagine you have an implant. They're great, they work really well. You can get, for example, like hip implants, mechanical heart valve, vascular grafts. They can really save your life. They can also get infected. And this happens more than we would like. There are around 500,000 infections every single year globally. And the treatment of these infections is like 500,000 crowns, so $500,000. Really quite expensive. And worst of all, the mortality is super high. So if you have a mechanical heart valve and you get a bacterial infection, the mortality rate is 45%. So it's basically like flipping a coin, see if you live or you die. Pretty scary, especially because I'm getting a mechanical heart valve in around 20 years, so not a nice number for me. If you get a vascular graft, it's actually even worse, 53% mortality. So that's really something to make better here. And the reason for these issues is that bacteria can attach onto the surface of these implants, where they can form a protective biofilm, protect them from our immune system, protect them from the current antibiotics. And to make things even worse, there's something called persister bacteria. Basically imagine bacteria, but they have fallen asleep inside the middle of this really nice gooey substance around the bacteria. And when they're fallen asleep, we just simply can't kill them with the current antibiotics. So that means that right now, if you have an infected implant, you'll treat with some type of antibiotic, you'll kill the active bacteria, which is great, But these persister bacteria, they will, as the name suggests, persist. And when you stop treatment, they will still be alive, they will wake up, repopulate the biofilm, and then you have the infection all over again. And you are still sick. So you think, new antibiotic, sure this works, but no, same thing, try once again, and the cycle just continues, and as it continues, the antibiotic resistance also increases. So it's bad for you and also bad for everyone in general. It just leads to a situation where the only thing we can really do is try to take out the implant, and that's really not an option if you have, for example, a mechanical heart valve or a vascular graft. And that's what leads to these types of infections being so costly, being so deadly. And what we want to do, our ultimate goal, is to develop a new drug that can kill these persistent bacteria. Because if we can do that, that'll be the key to finally eradicating these biofilm infections. So we stop this endless cycle, leading to cheaper costs and better patient health. And that's the dream. How do we do it? Well, actually, drugs that kill these persistent cells, they already exist. We have our own favorite. It targets the DNA of bacteria. Really great. Only problem is, we also have DNA, which means that it is quite toxic to our cells as well. And that is where our solution comes in. So we want to do what's called targeted delivery. And let me tell you what that means. It means that we use what's called a targeting agent. So you can imagine that as a little Lego guy. He sees the infection and then he actively moves towards the infection. And then we want to use this Lego guy to deliver an anti-persistent antibiotic. You can imagine that as a sword. You know, if it's just lying around, it's quite dangerous, you can step on it and stuff, but then you can also use chemistry to put this sword in his hand, and then you suddenly have a drug that can actively kill the bacteria while not just poking random holes in your body. Yeah? So the idea here is that this new drug can find its way to the site of infection. Here it will go to the bacteria, go to their surface, and it'll be ready to attack the bacteria, kill them, and hooray, we solved the infection. Now this is really great because it means we can finally use these anti-persistent antibiotics without worrying about them being so toxic. Because we can do that, we actually have a chance to eradicate the infection and not just suppress it. And now let's go to the chemistry. So, because I am a chemist by heart. So when I put up this cool little Lego figurine, what I really mean is this guy. It's called vancomycin. A little bit less nice to look at, I would say. Well, for you guys, for me, it looks beautiful. The little sword is actually called mitomycin C. It looks like this. Here it's colored purple because it's nice, beautiful, and purple. In real life, purple and deadly. And then the full drug looks like this, has a little linker in between to couple the two things together. Yes. Now, when I usually give a talk, this is also the kind of figures I would show. Every arrow is like a specific chemical condition, there's a lot of different compounds, and it can get really confusing when you're not a chemist. But again, it's just like having these building blocks and putting them together. So I might start by having a torso, then I stick on some legs, then I put on the one arm, then the other arm, then a head, give him something to stand on, and then put the sword in the hand, and then we are ready with a new drug. Now, really importantly, we need to figure out these drugs work. And that's why I'm very happy to have some awesome collaborators, such as Magnus, you can see in the corner, a little bit pushed up there. And she's a microbiologist, that means she can actually work with the bacteria while I just do the chemistry. And what we could do here was take the bacteria, we can then add this new experimental drug, let it just find its way to the bacteria, then we'll wash away anything that's not on the bacteria, and then we can measure the bacteria. All right, I'll just take you through this graph. On the x-axis, we have the concentration of the drug that we are administering here, and on the y-axis, we have how many, or the reduction in the amount of bacteria that survive. So at the top left, you have these white circles, that's just our control. No bacteria die, that makes complete sense. Then you move one step to the right, and you see there's a little bit of death here. Bacteria, fine. Then we increase the dose to 1 milligram per liter. And suddenly we see more killing of the bacteria. That makes a lot of sense. But if we move to just 2 milligrams per liter, we see that these black dots suddenly move all the way down here. And when they're below this line, it means we've killed 99.999% of the bacteria. Because this y-axis here, it is what's called a logarithmic scale. That means that we've not killed 2 bacteria and 4 bacteria. It means we've killed 99% of bacteria and 99.99% of bacteria. So this is quite potent. And 2 milligrams per liter is probably a little bit hard to, like, how much is that? Imagine the tiniest speck of dust you can barely see with your eyes, and you pop that into a liter of milk, and then you kill 99.99% of all the bacteria. Quite potent, right? So this compound, this targeting agent, vancomycin, it has multiple different places where I could put this drug. And you can kind of say it's like if you have the Lego figure, you can put the sword in the left hand, put the sword in the right hand, you can stick it in the foot. And we propose that maybe there's a preference here. So we can call these different sizes foot, left hand, right hand. And then our awesome microbiologist does this experiment again, treating this bacteria with the drugs, all 3 different drugs. We have a similar graph. Again, this is the amount of bacteria or reduction in the amount of bacteria that survive. We see the control at the top. It makes sense. Then in the foot, we do see a reduction, but it's not what you would call statistically significant. You'll see this stars here for the nerds. It's like, oh, are you sure there's an actual effect or not just an artifact? This just means that we are not sure this even like a real effect. But if we use the left hand instead, the left hand, we suddenly see a little star. That means that this is working better. Now we're actually seeing an effect of the drug. But if we use the right hand, suddenly we see it works much, much better again. So we can really conclude from this that our little figurine is right-handed. And figuring this out, this means that we've now, just by changing the chemistry of the drug, we've made the drug much more potent. Now if we compare this with just taking the sword and just stabbing it directly into the bacteria without any targeting, this is now actually more effective with this targeting agent that removes the toxicity. Remember, that's why we're doing it really. But it's also now more effective than just using the sword on its own. So it's really pretty good. Next up, it's awesome to be able to treat one type of bacteria, but can we treat more than just one? So we picked some different types of bacteria, MRSA, VRE, Epidermidis. These are just some really dangerous pathogens that you really don't want to get an infection by. And our drug, no problem, it took care of all of them. So that was a really nice experiment. So this is what we call a broad spectrum antibiotic. You can hit a lot of different types of bacterial strains, and also a lot of other pathogens that just, it would be too big of a slide. I'll spare you the detail on the data. Trust me, it works. Now we went back to the chemical drawing board, so to speak. And we thought, okay, this works really well with this compound called vancomycin. But there are other compounds that kind of look like it. Other things we could use as target agent. So we found this one, and also this guy here. And then I went to the lab, I synthesized these new potential drugs. And what we saw was, again, really good activity for the first one. But we then changed to the second one, great activity, it looks even better. But the third one, incredible. Suddenly the drug was more potent than we would have imagined that it could become from the beginning. That is awesome. So just by changing this targeting agent, I actually made it even better than before. Now we thought, this sword works pretty well, but what if we give him a dagger? How would that work? So here we changed the anti-persist antibiotic from the one I showed you previously to another one that works in a different way. And while we saw incredible activity for the first one, we also saw incredible activity for the second one, but kind of in a different way. Not necessarily better, not worse, just different and very interesting. So this really shows that what we have here is a drug platform that can really be varied a lot. There's a lot of potential in many different ways. So where do we go from here? Because this all looks very promising. Well, I can tell you, statistically speaking, the chance of what we're doing here, making it from where we are now to actually saving the patients, less than 1%. And you know that doesn't sound great. It's not like awesome odds. But if you flip it on its head and say you have 1% chance of helping 500,000 people every year struggling with deadly infections, I'd say I'd take those. I mean, that sounds pretty good. If you really, no chance, but really, truly a high impact. With that, I'd really like to thank all my collaborators, my supervisor Alex, collaborator Rege, the people who did all the bacterial experiments, the lab, our clinical collaborators who are doctors and stuff, and of course also about funding. There must be forskning for minorities, and I would stop here, but there's also one more important little point. As you can see, also during the presentation here, this is quite interdisciplinary. You know, I'm a chemist, and if it were just me, I would make some molecule, and that would just kind of be it. It wouldn't really be used for anything. It wouldn't be very interesting. That's why it's so important for us that we can collaborate with people from different backgrounds, here microbiology and as well medicine as Skype. And that is made quite a bit easier at Aarhus University because we have this interdisciplinary iNano center. We have this interdisciplinary iNano center. In case you did not know, they are scrapping this interdisciplinary center that has been making groups like us, been making our lives easier. And I think this is something that the general public also should know, because this is kind of a big deal that a lot of students and a lot of staff are very unhappy with. So I thought you should all know this. You should all be upset on our behalf, on your own behalf. And if you know any journalists or anything, contact me and I'll contact some people who are better suited to take this further. Yeah. So that's what you know. And then I go back to the positive side.
Thank you so much for a great talk. And also thank you for highlighting that it is extremely important that the public also support us in what we do and support collaborations, because it's very expensive for universities. They don't really care, but it does make a difference to people. It makes a difference to you. And with that, I will take any questions for comments. Come on, guys, somebody's got to ask him about the fire. Why were you set on the fire? Hey, go.
What makes it only have a 1% chance at success?
Well, I think you know, when you write something up, you have a great idea. You see all the possibilities, but in reality, biology is incredibly complex, and there's so many things that can go wrong. For example, we could see great effects in vitro, when you just have the bacteria in a little plate and you try to add the stuff, but then when we put it into mice or humans, we might see that it simply does not make it where we need it to be. And these things can be really hard to predict. It could also be that then we move on to the next stage, and suddenly we see that it just doesn't work as well as we had hoped. Then we move on to the next stage. Maybe it just turns out that there's actually some really deadly side effect that we just cannot live with. So there's a lot of steps to get through, and every step there are like 10 things that can go wrong. Also, like more stupid things like, oh, the person who was the main driver of this project suddenly got sick or found something better to do. And then that just, you know, when there's so many steps where there's a pretty high risk of failure, the overall risk of failure gets very high, unfortunately.
I have one. So you said that when you add the targeting sulfoglamicin,
Yes.
You see more activity. Why would you think so? Because you are just doing like in vitro, right? So
Yes.
so why would you think that just by adding that it will be more effective in this case?
So it makes sense because, we actually have better data for this now as well. But for this experiment where it's more effective, what we do is that we add the drug, let it bind, and then we wash away things that's not bound. So if you just add the drug and then wash it away, it'll have a little bit of effect, but you also wash away a lot of it. But here, because we are kind of attached to the surface of the bacteria, we don't wash anything away, and then it works better.
Okay, yeah, because I was just wondering, because like in the human body, like it would target, but in this case, it's just like you just have this like
So in
vitro
the body
situation.
will also make more sense because that's a constant flow.
Flow,
for the
okay,
science.
it's because of
So,
the okay.
Yeah, so their normal drugs would be kind of flushed around all the time, and then sometimes it would reach the site of infection, right?
Yeah.
But here, when you reach the site of infection, you would kind of stick to it.
Yeah.
So that's also why we would assume it would, it's like that it would work better besides having lower toxicity.
Okay.
And also, you know, when you have a drug, and that's like a lot of, or very few bacteria, but very few drugs, can like have to find each other. But then with that's targeting, it's easier for them to find each other. That can also actually also make drugs more potent.
Okay. Thank you.
Yeah.
No, I'm going to ask that. Okay, so in some of your evidence, I'm not sure if it's just the way that it's like depicted. The bacterial cultures are completely homogeneous, right? So it's like one type of bacteria that
Yes.
but that's not the case in the the problem that you're kind of targeting, right? So is it possible that these biofilms, they have some kind of special friendship going on between different kinds of bacteria that makes them so difficult to
Yes, that happens.
target? Or
For sure, that's also, I mean, it is well known that they are, a lot of them are multi-bacterial bacterial colonies.
Yeah.
But that's also why it's so important that we show this broad spectrum of
Yeah,
bacteria.
sure.
So, and I didn't go too much into detail with this because of time and stuff. But we actually see that we're using this drug called vancomycin, which is actually an antibiotic on its own. We're using it like as a targeting agent, right? We think it's to direct. But when we take then bacteria that are resistant towards vancomycin, so it shouldn't bind so well, if at all. The drug still works when it's just a targeting agent. So even against the bacteria that have developed this resistance against the thing we're using, it still works when we do it like this. Yeah. So that also shows that it's much more potent than it would be otherwise.
Go for it.
Yeah, you mentioned because in the human body there are like a lot of different like hip implants and mechanical valves in the heart. Have you in any of your models yet researched about which ones that are best suited for treatment?
No, that's very important. So we wish to, target the ones that are the worst. So that would be mechanical heart valves, vascular grafts. So that is what we kind of like we want to treat. But at this point, it's like we just want to treat anything, really. So we take whatever models we can get, and it's also like a practical thing. We have some awesome collaborators that have a model, and when that's the model is up and running, that's the one we're kind of trying to solve. Because otherwise, we need to find other collaborators. We like the ones we have. But we also have different models in mind. So we have like at least 3 different models that we right now looking into testing. It's all in vivo.
Are you right now doing any research on, because vancomycin binds gram-positive bacteria, right? Are you doing any research on gram-negative like sort of monomers?
Yes. So we actually tested against gram-negative bacteria as well. And we would not expect the bacteria like either gram-positive, gram-negative. It's like a difference in what the outside of the silicon looks like. Their barrier to the outside, so to speak. And gram-positive is like what we expect this to work against because of the way we designed the drug. Works really well. I think gram-negative we expect it to not work at all, or at least much worse. It doesn't work as well, but it actually works against the gram-negative as well. Interesting enough. Not so much that would be like, wow, this is the perfect drug against gram-negative bacteria, but it actually does work. So, for example, we have a biofilm that has a mixture of gram-positive and gram-negative. I would expect them to also be at least decently effective against gram-negatives.
How long do you treat the bacteria? So you said there are these persistent ones that come back. So how long is the experiment?
So for like the persister cells and the treatment coming back and stuff, that's more for like in vivo. For the experiments we've done so far, which are called in vitro, it's in a petri dish. We only treat for 15 minutes. So we add the drug, wait 15 minutes, and then we wash it away. And then we just let the bacteria sit for 24 hours, let them be killed, and then we measure after that. So time for binding, only 15 minutes, and that's enough.
Yeah. So what's going to be your next step? So are you going to use different targeting agents, or just move into in vivo like trials, or what are you going to do next?
Both.
Okay.
Yeah, so we've done different targeting agents. I think we've kind of done that part. We have now 2 different anti-persistent antibiotics. They're also working. It's very interesting. So we are also kind of done some stuff there. Then that's the chemistry that we use to put them together. We are doing work now to kind of see if we can tweak that to make it even better. Because so far every time we change something, we make it better. But otherwise, I'm just making quite a bit so we can kind of push it into the mice and see if it actually works in them.
Has anybody tried to make, so the problem is with the biofilms being on implants, right? Has anybody tried to improve the material of implants so
Yes.
that they don't get the biofilms stuck in the first place? Is that not like the obvious
Oh yes,
first
for
way to
so many years, and it works great in papers.
Okay, no, it's annoying.
But they've never made it past the papers.
Okay.
And I think there are multiple reasons for this. It's a great idea, and people have done some incredible science in this, for sure. But it's just not easy to translate. That's also like a simple fact. You need to do what's called a clinical trial, or just to like scientifically say this is working. Now, if you have an infection and you then give our drug, for example, you kind of try to see, are there any of these patients we can cure that we cannot cure without it? And that's kind of like a positive result, right? If you want to make a new implant type material that's where you expect the infection to be more rare, well then the risk of infection is already at like 1%. So then you have to reduce that from 1% to maybe like 0.1%, right? And you have to do this by finding so many healthy patients that are willing to get an experimental material inside their body that has maybe not been tested so much in humans before. And it's just not practical. I mean, you need so many people, and it would be so wildly expensive that it's just very difficult to get it.
I can keep asking.
Yeah, I can
People
also-
should,
I can also for your in vivo trials, would you first try just to see how it distributes in the mice, or you just go directly to try to see the effect?
We actually, so we have done some in vivo work already. We went directly to see an effect. Hasn't worked so far, so now we actually take a step back and kind of see distribution.
Okay, yeah, because like normally, I mean, I didn't work with this, but I was trying to, I did some drug development, but it would always like stop at the phase of the testing the distribution in mice, because it's so difficult that it gets to where you want to.
Yeah, it is difficult. I mean, we have the advantage here that we're using drugs that exist, right?
Yeah,
So
that's a good.
we already know that the drugs, each of these two drugs on their own, they make it to the infection. So when we put them together, surely they'll also make it to the infection, right? Nothing could go wrong.
Have you considered other indications like, 'cause I mean, implants is super interesting, but right now like some intestinal diseases like Clostridio, they're like treated with vancomycin at the hospital right now, but have a very high mortality. And like, have you considered other indications?
I do not know this one. Is it a biofilm? Do you know?
No, but like it comes after long-term antibiotic treatment in the intestines, and it's right now treated with vancomycin. So I was just thinking, like, if your drug is more effective, then that's an interesting approach as well.
For sure. But we're also looking into it. Yes, I have to be a little bit careful sometimes. We are looking into other things as well. Like so we are patenting this, and if it doesn't say it in the patent, I shouldn't say it. I'm not sure if this part is technically in the patent, so just be safe. I would say yes, we can consider it.
To follow up this the question, so you haven't looked at the intestine, but you have also biofilm in oral. You have some oral disease.
Yes.
Are you going to do some essay for that?
We could, but the thing is, from our oral cavity, you can just reach in there and remove it. And the drug, we are removing a little of the toxicity from it by making this targeting, but it's still a little bit toxic, right? It's not going to be a drug that you want to take if you have something in your teeth. It needs to be something that is very unpleasant, if not life-threatening. Otherwise, there will be more simple treatments that will be enough, or it will be better. Unless we see that it just works so well and there's no, problem at all, we see no side effects, but that's, minimal. So it makes more sense as a drug that's against like really, really deadly things, or really things that really need to have some kind of treatment for, but don't have one. One more question.
So the bacteria in the films that stay dormant and then somehow regenerate, is it specific types of bacteria, or is it some property that any old bacteria could acquire?
They are. It's not, as far as I remember, it's not all bacteria, but it's a lot of bacteria able to form biofilms. And you see it for a lot of the really deadly kind of well-known bacterial infections. I think it's actually quite a lot of infections in general that are biofilm infections, because they are just the ones that are most difficult both for your body and for people in general to kind of get rid of. And the persistent bacteria, just in case you also asked about that, in the middle, the reason they kind of go dormant is like it's the same bacteria, it's just when it's in the very middle there, all this gooey stuff, it also gets really hard for nutrition to kind of get into the bacteria, so it gets nothing to eat. And then, when you get nothing to eat and there's no, you just kind of fall asleep because you have no energy. That's really what happens.
So it's hibernating, basically.
It's basically hibernating,
Okay.
yeah, very much.
Nobody else? Nobody, you're going to have to tell us about this.
Sorry.
Yeah.
Sometimes you have fun facts that are technically correct, but actually not that fun maybe when you tell them. Sometimes like a mystery.
We will laugh
I,
anyway.
alongside two people in this room, went on Animal Ian, it's a primetime Danish TV show with something called Chemistry Show. It's like we toured Denmark and made fire and explosions and stuff. And then this is stuff where you put lighter fluid in soap bubbles, pick them up, and then just light them on fire, and you like lit each other on fire.
Well,
It was fun.
doesn't seem very pleasant.
It is actually a little because you have this water, so you like kind of douse yourself with water beforehand, and then like it doesn't hurt at all. You just stand there like your whole arm burning. It's great. It's very cool. I recommend it for anyone with a trained professional.
Nice.
Did you tell your grandma to turn the TV on?
I should have.
Yes, I think if we don't have any more questions, so thank you again.